In this lecture, we're going to talk about conditional probability and independent events. Let's start with a definition of conditional probability. Here we have a special symbol. This P, this probability function with A and the vertical slash and the B, that denotes the probability that the event A occurs if we know that the condition B obtains. Okay, so if a condition obtains, that means that it's happening. We read this as the probability of A given B. So this right here is the probability of A given B. That's how we read that. So we look at the world here. The yellow denotes sample space. A here in red denotes an event, and B over here in blue denotes an event, and they have an intersection. So with A given B, we assume that B has happened. Okay, so now we've moved into a point in time where B actually has happened, and so B is our whole sample space. B is our whole universe, and the only part of A that is left is the part of A that is inside B, which we write, of course, as A intersection B. Okay, and so we can then have a conditional probability formula. Right here, our conditional probability formula, that the probability of A given B is the probability that both A and B occur divided by the probability of B. Now, mathematically, how can we justify this? Well, we work do a special case known as equally likely outcomes. We let X denote the number of outcomes in A intersection B, little b be the number of outcomes in the event B itself, and X be the number of outcomes in the whole sample space. Okay, so the probability of A given B, well, that assumes that we know that a whole sample space is B, so that's X divided by B. Then we divide numerator and denominator by capital N, and so that gives us that our numerator is the probability of A intersection B, and the denominator is the probability of B. Okay, the main reason we're interested in conditional probability is that we're going to be talking about independent events when we go to talk about the binomial probability and the binomial distribution. Now, intuitively, the event A and the event B are independent of each other if A obtaining has no effect on the probability of B and vice versa. Okay, so mathematically, the probability of A is just equal to the probability of A given B, and the probability of B is equal to the probability of B given A. Knowing that we have this condition or this condition does not have any probability on effect on the probability of the other. Okay, so intuitively, that's what independent events are. When we test for them, we have a very simple mathematical test, and that is if the probability of A intersection B is equal to the probability of A times the probability of B. Okay, and so this is if two events are independent, this is true, and if this is true, the two events are independent of each other. This is the exact time that events are independent, as if this is true. Let's do some mathematics to justify this. The mathematical justification, well, let's make the assumption here that the probability of A is equal to the probability of A given B. Well, we did the calculation earlier that the probability of A given B is equal to the probability of A intersection B divided by the probability of B. That's our conditional probability formula, and it's always true regardless of whether the events are independent or not. Okay. So with that, but that gives us this is equal to this, and so I can multiply both sides by the probability of B and get this right here. Now, the cool thing is this formula here, excuse me, that's not the one. This formula here is symmetric in A and B. I mean, we switch A and B around, we get a nice formula, and we can then, if we switch A and B here, we can still prove this by the same algebra. So if the probability of A is equal to the probability of A given B, then the probability of B is equal to the probability of B given A. It's quite cool.